Let's go ahead and look at this problem. So this problem, we're considering the horizontal displacement of a pendulum from equilibrium, where that horizontal displacement is in damped harmonic motion. We're given some of the qualities of the damped harmonic motion, including its equilibrium position, time t equals 0, its initial amplitude, its quasi-period, and its damping constant. So let's just go ahead and identify the parts that we're given here. So see that the pendulum is at equilibrium at t equals 0. This tells us we're using a sine function with an initial amplitude of 30 centimeters. This is telling us our k value is 30. Our quasi-period is pi. This is telling us that 2 pi over omega equals pi, or that omega equals 2. And our damping constant is 0.02, which tells us that our C value is 0.02. So note that our equation for d of t is not totally determined because we don't know if we're increasing or decreasing or moving to the left or the right at t equals 0. So really we have a little bit of ambiguity here that we can work with. So determine an equation for d of t. Well, both the equation, the positive or negative of the expression 30 times the sine of 2t, oops, excuse me, that's incorrect, but rather plus or minus 30 times e to the negative 0.02t times the sine of 2t. Both these equations would model, either the positive root or the negative root would model this behavior, again because we're not given an initial condition for motion. So both these would work for an equation for motion. Just for the sake of plotting d of t in this next example, why don't we just plot the positive version of this, an equation that would work for d of t, the positive of 30 e to the negative 0.02t times sine of 2t. So to plot that, what do we do? Well, we could consider first putting in our rectangular coordinate system. Now note that when I plot any graph for an object in simple harmonic motion or damped harmonic motion in this case, t starts at t equals 0. We don't really consider our time before t equals 0 before we start observing our system. So here we'll start time at t equals 0, only plot a graph for domain t greater than or equal to 0. I know that its initial amplitude will be 30 centimeters, so I'll mark 30 and negative 30 on my graph. Then I'm going to mark, or graph rather, these functions that bound d of t equals 30e to the negative 0.02t sine of 2t. So again, note that the sine of 2t, by our discussion of variable amplitude graphs in a prior class session, we can see that, well, sine functions are bounded above and below by negative 1 and positive 1 respectively. And so this function d of t should be bounded above by positive 30e to the negative 0.2t. Maybe that graph looks something like this. So let's plot that y equals 30e to the negative 0.02t. And then let's also look at the bound below. And that bound below would be y equals negative 30e to the negative 0.02t. And so with both of our bounds, noting our quasi-period is pi, so let's say that's our first quasi-period, this will be our second quasi-period. I'll break those quasi-periods up into 4 or 5 important evaluations, whether you include repeats. We'll note some things here for us so we know that the we begin at an equilibrium position. We know that we're modeled by a sine function. Again, I'm going to plot that positive root here, so we'll increase to a maximum value at, say, a quarter of the way through our period or our quasi-period, which is pi. A quarter of the way would be at pi force. See, I can construct the rest of this graph just by our ideas from variable amplitude graphs, and we look something like this. So we want to answer ourselves the question. Oh, let me get a box around this graph now. So we also want to answer the question, describe the behavior of a pendulum as time goes on. So as time goes on, that's basically saying as time goes to infinity, or goes infinitely in a positive direction, the only way that time tends to go, what is the behavior of our pendulum? And here it's clear to see from the graph of our function that as t approaches infinity, d of t approaches 0, or the pendulum approaches rest, and that's what we'll say here. Or pendulum approaches equilibrium position. Approaches equilibrium position. Or we'll just say approaches equilibrium. And here we have our behavior of the pendulum as time goes on. Again, this is really just asking you about the end behavior as t goes to infinity, where we see our graph is approaching 0 as time goes on, and therefore our pendulum is approaching d equals 0, or its equilibrium position.